Welcome to our discussion on linear inequalities in two variables. We've only got two objectives. We want to be able to graph these inequalities and then solve the systems of inequalities, either by looking at the graph or with other means. So we know the graph of y less than x will consist of all points that have y coordinates that are less than the x coordinate. And the graph of the region y less than x can be found by just graphing the line y equals x. And you graph it as a dashed line because the inequality is a strict inequality, right? It's not a less than or equal to. And then that line separates the xy plane into two planes. You can think of it like two halves, where y is less than x and y is greater than x. And we can figure out which half is the solution by merely selecting a test point. Any point that's not on the line, pick an easy one, with zeros in it is always the best. Zeros and basic numbers. Plug it into the inequality, and if it's true, you shade that side of the line. So for instance, here's the line y equals x, is a dashed line, right? It's a nice 45-degree line, 45-degree angle line, goes right through the origin. And if we're doing y less than x, we can pick this point 2, 0, plug it in here where x is 2, y is 0, and it's true that 0 is less than 2, so we know that we shade this half. Now it's pretty obvious if we're looking for values where y is less than x, it's going to be below the line. But as these lines get more complicated as far as, they're not going through the origin and they're not just simply y less than x, there's maybe a 2x plus something, there's more to it, then you still want to use this technique. You graph the line like normal. All you got to do is find 2 points that satisfy the line as if it weren't equals. Connect those dots with a dashed line. You can do a solid line, again, if it's a less than or equal to or a greater than or equal to, right? But if it's a strict inequality, you do the dashed line. And then you just pick any test point on either side of the line, plug it in. If it's true, you shade that side. If it's false, you shade the other side. So for example, 0, 4 didn't work, and that's why we didn't shade on that side. Okay, let's look at another example. We've got 4x minus 2y is less than 6. First thing we do is we think of less than or equal to 6. First thing we do is we think of it as an equals, right? We want to think of it as a normal line. Now, if you want to, if you use the technique of just a data table, where you go, okay, here's my x, here's my y, and I'm going to plug in some values. So if I let x equals 0, then I get negative 2y equals 6, and then y equals negative 3. And then if I let y equals 0, this goes away, and I get 4x equals 6. So x equals 6/4. It's not really easy to graph, so it's better off to try and pick something that will, actually give you whole numbers, because then you can graph them better. But, this 6 divided by 4, like we said, is 3 over 2, which is 1.5. But if you don't want to hassle with graphing this, then you have to just keep picking kind of random numbers until you get one that works. So for instance, if you let y equal 1, then this becomes a negative 2. You add 2 to the other side, which makes this an 8. And lo and behold, that gives you a 2. So those are the two better ones to graph. So then you come along and you graph your line. Well, here's the 0, negative 3, and the 1.5, 0 number, right, that we found. But you could also go 2, 1. You can see that would be easier to graph if you had, the actual grid paper. But in any case, we do the solid line, because this original one was a less than or equal to. And then all we have to do is pick a point and test. And if the line doesn't go through the origin, then of course the origin is always the easiest one to choose. Now in this example, we rewrote it in y equals mx plus b format so that it makes it, easier to graph maybe, because in that case you could just graph the y-intercept and then know the slope is 2, go up 2 over 1, and there's your next point. That's kind of nice. But if you left it like this, it's still just as easy. You plug in 2 zeros, right? Well, we're back up to here, 2 zeros, and 0 is in fact less than 6. So that's why we shade in the direction of the zeros. So that's basically it for figuring out your zones of shading from graphing and test points. If we have two or more inequalities in two variables, we can find the solutions that satisfy all the inequalities, and we call the inequalities a system of inequalities, just like you may have learned earlier in your math career how to solve a system of equations. We're now solving a system of inequalities, and it's relatively the same technique. So here's an example. We've got these two inequalities. First thing we're going to do is graph the two lines, right? The first one's going to be a full line. The next one's going to be dotted. We can do the table technique again. I don't know about, graphing this whole 4/3 0. I'd probably try to find another value of x and y that would work. So for instance, if we did y equals 1, and you'll notice that I always just try things close to 0. So if 0 doesn't work, then I'll try a 1, a -1, a 2, a -2. Right, I've already got the -2 there. So I put a 1 in here, which makes us a -2. So we add a 2 to both sides. That gives me a 6. And then, of course, if I divide by 3, x becomes 2. And I think, x becomes 2, not an x. I think that's a lot easier to graph than that. But in any case, there are the two lines. Okay. So now we have to figure out in which direction each of the lines shade. Well, you'll remember that here are our two original lines. Neither of them have 0, 0 in them, so that's the perfect test point. So I plug 0 in here, and I get 0 greater than or equal to 4, which is false. So I know that this one's going to graph in this direction because it can't include 0, 0. Then I try this one, 0, 0. So then I get -3 greater than 0, which is also false. So I know this one shades in this direction. And then you can see this is where they're both shaded, where they overlap. So that's going to be your solution region, we like to say. It's the area that solves both of them. So here it is with more formalized lines, right? And then there's that region. How about an example that actually has a real-world context? So we have an appliance company, assembly plants in Atlanta, Fort Worth, where the company produces a variety of kitchen appliances, including a 12-cup coffee maker and a cappuccino machine. At the Atlanta plant, 160 coffee makers and 200 cappuccino machines can be assembled each hour. At the Fort Worth plant, they can do 800 coffee makers and 200 cappuccino machines in each hour. They expect orders for at least 64,000 coffee makers and 40,000 cappuccino machines. At each plant, the number of assembly hours available for these two appliances is constrained by each plant's capacity and the need to fill the orders. So we can write the system of inequalities that describes these plant constraints and then graph the solution region for the system. So this is always a good idea to put everything in a table just to kind of organize your thoughts. So the two different makers, right, coffee, cappuccino, the two different factories, and how many they can do per hour in each, and then how many are needed. And the table and the fact that both x and y must be non-negative gives the following constraints. That 160x, right, so it's basically, I can do 160 of them per hour, so this is x is number of hours spent in the Atlanta factory, plus 800y, right, where y is the number of hours spent in the Fort Worth factory. That needs to be greater than or equal to 64,000, right, because they need to produce at least that many. What do you think the second sentence or statement's going to look like? Well, how about the other one of the 200x plus the 200y has to be greater than or equal to 4,000. Remind yourself, right? 200x, 200y, 40,000. So there are two constraints, plus we have the basic constraints that x and y have to be greater than or equal to 0, because remember, x and y are representing hours of production in each of the factories, and you can't have negative hours of production. Oftentimes with these real-world examples, we always have the added constraints that the x and y values both have to be greater than 0. So now it's a matter of graphing things and shading them in. So you can see that our shade stops at the x-axis because y being greater than 0 means we're only to the right, and x being greater than or equal to 0 means we're only above. So here's our first line, and we have to be greater than or equal to 64,000. So if we do the test of 0, 0, we can see 0, 0 is not greater than, so we shade in the other direction. Then we bring in the second line, do the same thing. Of course, 0, 0 fails, so we shade in that direction, and we get this region of solutions. Now, the nice thing about when we're trying to find maximization and minimizations of these equations, these systems of equations, or in this case, inequalities, is we know that maximums and minimums always occur at vertices where, lines intersect. So this is a vertice because it's where the line intersects the y-axis. Here's a vertice, right, where the two lines intersect, and here's another vertice. So you just have to you have to check those three vertices. So now it's just a matter of kind of figuring out which ones work best. Now, if you can, you always want to reduce your equations, because why work with big, huge numbers when you can divide everything by 10 and then even go further, right? They're all divisible by powers of 2. You can get this all the way down to x plus 5y equals 400. And this one, divide both by 200, you get x plus y equals 200. Much easier to work with. So now we can use the points to determine which ones work best. Now, if you didn't know how to find this corner, right, where they intersect, and if you don't want to try finding it by using a graphing calculator, because sometimes those can be less than accurate, you're basically back to our technique of solving a system of equations, which means you have to either use the elimination method or the substitution method. Here is reminding you how the substitution method works. Well, it's actually the elimination method, I'm sorry. We subtract the bottom one from the top one. The x's go away. You're left with 5y minus y, which is 4y. 400 minus 200 is 200. Divide both sides by 4, and you get y equals 50. Once you know what y is, you plug it back in. If y equals 50, then x has to be 150, and that's how we get the solution of 150 and 50. And then in later lessons, we'll see how we can determine which of these vertex points will maximize our revenue, because we'll have to have a revenue equation as well. All right, that's it.